Okay, it's wonderful to have Sivakanth Gopi here from Microsoft Research, who's going to be telling us about DP-SGD. He was supposed to speak a few weeks ago, but due to a scheduling screw-up, he's speaking now.
That's fine.
Thank you.
Yeah, thanks for the invitation. It's good to be giving the seminar here. So I'll talk about our work on how to make differentially private SGD faster and also more memory efficient using JL projections. This is joint work with my colleague Janathan Kulkarni, and Yin Tat Lee, Ziki Bu, Judy Han Shen, and Uttapanta. Okay, so I guess I don't need to convince you that we should train. While training neural networks, we should be careful about the privacy implications, because neural networks can memorize data almost verbatim, like this XKCD comic predicted, and people actually verified this also experimentally on real-world models. There's this paper by Carlini et al. Where they actually say that unintended memorization is unavoidable almost, and differential privacy is almost the only technique they know which led to solving this issue, although it loses in utility. Okay, so we don't really have many other methods to train neural networks in a private way. So this is an important problem to how do we train neural networks using differential privacy. So I guess most of you are already familiar with differential privacy, which is anyway, let me just briefly say. So what we want is user level privacy. What that means is, imagine you remove one user's data from the training data, then the model that is trained in adversary, which looks at the model, should not be able to tell whether this user was present or not. Okay, so this is the definition, and there are two parameters, epsilon and delta, which tells you how close the distributions of the two training models are, and the smaller the epsilon and delta, the more private our algorithms. Okay. So I would argue that this differentially private deep learning is really the holy grail of private machine learning. It's because just because deep learning is the most important thing in machine learning, and how do we make it differentially private really opens many doors in private machine learning. So there are two main goals in this area. So the first thing is, how do we achieve good privacy versus accuracy trade-offs? So as you can see, there is every differential private algorithm will have this trade-off. Okay, if you are willing to incur more privacy loss, you can get more and more accurate. So there is this tension between how much privacy you're leaking versus how much accuracy you can get. And the goal the main goal of this area is to improve this trade-off curve. And the other goal is to make differentially private training as close to non-differential private training, the usual deep learning, in terms of resource costs, like how much time you need to train, how much memory you need to train, how many GPUs you need. So this is the second goal, and these two are pretty important for if this technology is to succeed. And in this talk, I'll focus on the second goal, which is like how can we get a DP training closer to non-DP training in terms of resource costs. But broadly, these are the main goals in this problem. Okay, so let me start with a very simple recipe for making any algorithm DP. This is very cartoonish, but the first thing is you limit user contributions to some small amount. So you don't want one user to contribute too much data to the algorithm. So you somehow want to control how much each user is contributing to the algorithm, and then the second point is how do you, and then you add some noise to mask this user contributions. So these are the two main things in any DP algorithm. So let's talk about the main or the most famous algorithm for training neural networks using differential privacy. This is called the DP-SGD algorithm by Abadi et al. From Google. And this is like the main workhorse of the current training of neural networks using differential privacy. So let's try to understand this algorithm a little bit. So it does the usual SGD stuff, but it changes it using the recipe basically that I just showed you. So the first thing is, instead of averaging directly the per sample gradients, you first clip them. So what that means is you scale them to have norm at most sum bound C. So So if you don't want any gradient to be too big, so that when you average the gradients, that person's or that user's gradient dominates the whole batch. So you want to clip them to have some bounded norm. See, this is the limiting user contributions part. And then you want to add noise to mask the individual user gradients, per sample gradients, the clipped per sample gradients. So these are the main things. And then they prove that actually it works pretty well. It achieves decent privacy versus utility trade-offs, not great, but decent. And the main thing they did in this paper was how do we analyze this, the privacy of this algorithm. And they showed some it is surprisingly good in terms of privacy than people would otherwise expect. So what is the problem with this algorithm? So other than the privacy utility trade-off, there is also the resource cost. So how much time does it take to train a neural network using this algorithm versus a non-private algorithm? So the main problem with implementing this algorithm is we need to clip the per sample gradient. So in each gradient, so in a batch, let's say a batch has size 256. So you need to compute, you need to clip all the 256 gradients individually. What that means is you end up actually calculating all the gradients, per sample gradients explicitly, and then computing their norm, and then clipping them. And this destroys the parallelization that is built into deep learning training in most frameworks. So for example, most frameworks exploit the fact that we only need the average gradient. They don't even return you all the per sample gradients. They somehow, throughout, while doing the backprop and the forward propagation, they already know that we only want to return the average gradient and not all the gradients. So they use this to optimize their frameworks and to make it run much faster. But this fact that we want all the per sample gradients really destroys this thing and makes it really, really slow, like nearly 100 times slower. That especially if you have large batch sizes, this is a problem. And large batch sizes are actually good for privacy. So it turns out that if you plug in the parameters into this thing, the larger the batch size, the better utility versus privacy curves you can get. So typically, for DP training, you need to choose much larger batch sizes than non-DP training. Okay, so any questions so far? Okay. So what we do in this paper, we introduce a new algorithm. It's called DP-SGD-JL, and this JL stands for JL projections, Johnson-Lindenstrauss projections. I'll tell you what they are. They're just random projections. What are the main points? So the main advantages is that firstly, it works on any architecture in a black box way. So this is not tailored to a specific architecture. It's not tailored to like convolution neural networks or fully forward or things like, or RNNs. It's just a black box algorithm which can train any neural network. And in terms of memory, it is almost similar to non-private SGD. So it does not require much more memory. And in terms of privacy versus accuracy, it gets closer to that. It's pretty similar to DP-SGD, though I mean it does lose a little bit, or it's not exactly equal. It is slightly worse than DP-SGD, but it's much better than DP-SGD in terms of training time speed. And the way we do this is basically the issue that we want this per sample gradient norms. We solve it by approximating them instead of computing them exactly. Okay, so what we show is that you don't really need the exact gradient norms to clip them. It's okay to have an approximation. And then once you have this approximation of the per sample gradient norms, then you don't need to compute the per sample gradient norms exactly, because what you can do is you can scale the loss functions with respect to each sample using this estimates, and then do one on backprop. Then it'll automatically compute the average of the clip gradients. So somehow if you magically know the per sample gradient norms, you just need to do one backprop on some scaled loss. So that is the idea. So let's see what are these JL projections. So for those of you who are familiar, it's actually pretty simple. Even if you haven't seen this, it's just a random projection. So let's see a vector X in RD in a very high dimensional space, and you want to know its L2 norm. So now if you take a random direction and you project this vector onto this random direction, it's pretty easy to see that the the length of this projection is proportional to the length of this vector, right? So it's just it's pretty easy to convince yourself. In fact, if you compute the expected value of the square of the length of the projection, it gives you exactly the L2 norm squared for if V is a random Gaussian. So, and if you take multiple such projections and then average them, you can get better and better estimate of the L2 norm. So, so you can see that the distribution basically is determined by this chi-r square over R. So this chi-r square over R is chi-square R is the chi-square distribution with R degrees of freedom, and this is how the graph looks like. So as R becomes larger and larger, it becomes more and more concentrated around 1, and you get a better and better estimate of the true norm. Okay. So now the question is, okay, that's good, but how do we project the gradients onto a random vector? For this to work, we should have a mechanism to do this efficiently than just computing the gradients themselves. And luckily, there is something called a Jacobian vector product, which I think maybe not many of you are familiar with. So let me just go through this. So suppose we have a function from d dimensions to m dimensions, then we can form this Jacobian matrix, which is the all partial derivatives arranged as a matrix. And the nice thing about Jacobians is that if you have a function composition, then the Jacobian of the function f, which is composed of all the smaller functions, is just the product of the Jacobians, right? So and now you can ask, suppose I want to so this Jacobian matrix is usually pretty large, and we don't want to compute it all the matrix. What we instead want is we want to be able to multiply this Jacobian matrix by vectors on the left or the right. So that's so if you want to multiply it on the left, this is called the vector Jacobian product. And it turns out that this is exactly what back propagation is doing. It is multiplying the Jacobian of your function with the vector on the left. So it's U transpose J. So, and then because of this thing that this JF is just the product of the individual components, the Jacobians. So what you do is you first multiply with U transpose with the first one, and then you remember it, and then multiply with the second one, and so on. So at no point you're actually computing any Jacobians. You're just computing vector Jacobian products. And that's how it is efficient than computing the entire Jacobian. And this is the familiar back propagation, also called reverse mode autodifferentiation. So there is a less familiar analog of this, which is you want to multiply Jacobian on the right, and the algorithm is even simpler. It turns out that it's more easy to just multiply things on the right and then to remember this vector and then multiply this one and again and so on. And in fact, it turns out that this JVP, which is Jacobian vector product, is in fact faster than backprop even, and it requires less memory because you don't need to remember intermediate activations. You just go forward. You only remember the last layer, and then you can just remember the next layer and so on. So this JVP is a faster. It's not really analogous. They're different things. The one is multiplying on the left, one is on the right. But JVP is not so used, not as popular as backprop, which is the standard thing people do. But with JVP is also implemented in many auto differentiation frameworks, like even TensorFlow now or JAX, and it's actually more efficient than backprop. Okay, so now we'll use this JVP to compute this JL projections of the gradients. So how do we do that? So projecting per sample gradients. So let's say the loss function is L theta x. Theta is the parameter and x is the sample, or the user sample. So, and suppose there are B samples in a batch. So you form this function f of theta, which is just all the losses with respect to each sample in the batch. And now if you compute the Jacobian vector product of this function, then you're basically projecting the gradients, all the B gradients, per sample gradients onto this random vector B. Okay, so I'll just give a moment to just parse that. It's actually pretty simple. So this Jacobian is composed of the per sample gradients, theta L, theta x1, transpose, and so on, the gradient of L with respect to xb. And then you're just multiplying with V on the right. So that this is the Jacobian here. So you should just expect to see the projections of the per sample gradients onto a vector, any vector that you want. So what we're saying is it's pretty easy to project all the per sample gradients onto a random vector, on any vector that you want, and get the projections. And it's very efficient. It's even more efficient than backprop. Okay. So that's the algorithm. So let me go in. This is the whole algorithm. So it's actually a very simple modification of the original DP-SGD. So instead of computing exact per sample gradients and then computing their norms and use them to clip, what we first estimate the per sample gradients, estimate norms, and then use this. So the way you do it is by projecting the Jacobian on, or multiplying the Jacobian on the right by some random vectors, and then using them to estimate the norm of the ith per sample gradient. So let's say this is mi is the estimate for the norm of the ith per sample ith gradient. Okay, and now what you do is, instead of you do an implicit clipping where you scale the loss function. You define a new loss function, which is the old loss functions, but scaled with this clipping using this estimate. So some scaling to clip this gradients. And then if you do one backprop, what you get is the gradient of L tilde theta. Gradient is exactly the average of clip gradients. Okay, so you're doing some implicit clipping. So what the main message is that once you have estimates of good estimates of the per sample gradients, you can do an implicit clipping by just scaling the loss functions and doing one backprop. So yeah, so that is the algorithm. So, and this is really efficient. So this part of the code is as efficient as non-DP training, right? Because you're just scaling the loss functions and doing this. So normal non-differentially private training, you just assume that the scaling constant is 1 by b, but now you have, or just 1, now you have some other. So it's exactly the same. The only extra thing is estimating the per sample gradient norms. Okay, so just to recall, so the main idea is it's enough to approximate the per sample gradient norms rather than computing them exactly. And this approximation can be done using random projections. And these random projections themselves can be done fast using Jacobian vector products or forward mode auto differentiation. Then there is never a need to compute the per sample gradients exactly. And you can easily extend this to other optimizers like Adam or Adam-X or things like that. So, but in this talk, I'll only look at DP-SGD. Okay, any questions about the algorithm? Okay, so now we'll go into the privacy analysis of why is this private. I mean, intuitively it looks like it, but proving it is a little bit tricky. So in fact, the privacy analysis is like much more complicated than DP-SGD for a lot of reasons. The first reason is that in the sensitivity of the algorithm in each iteration is not really bounded, because we're not really clipping them with the exact norms. So what that means is the scale gradients might have much larger norm than what we expect sometimes. So it itself is a random. The sensitivity of of this thing is itself a random variable. It's not a fixed constant. So we can't analyze it like the usual Gaussian mechanism or something. So actually, let's recall how DP-SGD does. The DP-SGD privacy analysis is done by Abadi et al. What they did is, okay, each iteration is basically a Gaussian mechanism without subsampling, right? Because we clip the gradients exactly, so then it's exactly a Gaussian mechanism, and it's very easy to analyze its privacy. And then you get some amplification because of subsampling for each iteration, which is also pretty easy. It's not too hard to see how the privacy curve changes due to subsampling. And then you compose these privacy curves using moments accountant or RDP. Okay, Rayleigh differential privacy, the RDP accountant. So this is how broadly the privacy analysis for DP-SGD works. So, and what happens for our algorithm is that the first step and the third step both fail. So firstly, it is not a Gaussian mechanism because the sensitivity is not really bounded. And then the other thing is that the privacy curves, you cannot really compute them using the standard accountants, as I'll explain later, because basically the moments accountant computes moments of some distribution, and for our distribution, those moments do not exist. And similarly for the RTP, these moments are not bounded. So you cannot use the standard accountants. So that's why it is slightly more complicated to do the privacy analysis. So, but I'll try to go over the privacy analysis in detail. So let's recall that let's define the privacy curve between two random variables, x, y, as the supremum or all subsets, the probability that y is in S minus e to the epsilon times probability that x is in S. So this is the familiar epsilon delta curve. And for us, x and y will be like, x will be m of d and y will be m of d prime for adjacent databases. Okay. So, so the main privacy claim that we want to prove is for this subroutine. This, let's call this algorithm M, which is basically, okay, this is like one. So this algorithm is like one iteration of DP-SGD-JL. So imagine we have some vectors G1 to Gn. So think of n is more like the batch here, batch size, not the whole thing. So we are given some vectors in RD and then some clipping norms, some noise scale, and the number of GL projections R. So what we do is for each GI, we estimate its norm MI. So MI is an estimate of MI is an estimate for the norm of GI using this GL projections, which is like you project GI onto random vectors, you square it, and then average, and then take the square root. Okay. And then use this estimate to clip GI. So you're not using the real norm, and then you're adding Gaussian noise. Okay. So how private is this algorithm? This is basically, this is the analog of the Gaussian mechanism. But because the sensitivity is not bounded, we can't just use the Gaussian mechanism privacy analysis. Okay. So how private is this? So this is the main privacy theorem, where we show that this subroutine, the privacy of this random of this algorithm is upper bounded by the privacy curve, where you want to distinguish between these two random variables. So think of ZR is some random variable. In our case, it will be this 1 over chi square R, because we are scaling by so this each MI, the distribution will look like the actual norm of GI times the square root of chi square R by R. This is something we've seen before. So when you scale, when we divide by MI, this is what we'll get, this random variable, the inverse of this thing. But it's some random variable, which is a very long tail, but let's ignore that for now. Let's try to understand this, what is this thing? So it's trying to say that the privacy, the privacy curve is upper bounded by this privacy curve, where the adversary is trying to distinguish between these two distributions. And the distributions are as follows. You first sample ZR, and ZR is from a known distribution, and the ZR is known to adversary. So you tell the adversary what you sampled, and now either you sample according to n ZR, so the mean of the distribution is ZR by sigma, or it is just 0. So you already so basically you're telling the mean to the adversary, and the mean is sampled from some distribution, and then the adversary now has to distinguish between this shifted normal and true normal distribution. So this is the main part of the privacy proof. So let me go over like why how we prove this, and also notice that if I when R tends to infinity, that's kind of like I get exact norms. Then this ZR random variable is just identically 1, and you get the familiar Gaussian mechanism. So this is the Gaussian mechanism curve. So as R tends to infinity, this does tend to the Gaussian mechanism, and that's why the privacy of the whole DP-SGD-JL, as R tends to infinity, it will tend to the privacy curve of DP-SGD. As you use more and more great JL projections, you exactly get the privacy curve of the DPS.
So, quick question: are you able to get any differential privacy guarantees for this, or what's the framework?
Yes. You can't, because the moments are unbounded of the privacy loss distributions. You'll see that because you see that the ZR has very heavy tails. So it means that this distribution will have like a heavy tail. and it'll only have, you can prove that the privacy loss distribution will only have moments up to r/2 and not beyond that. So you can still get something, but not the optimal bounds using this renewed RDP framework, because you can't really optimize over which moment you take.
Maybe I'm jumping ahead, but how would you do accounting?
I'll get back to that. Yeah, so I will show you.
Right.
Yeah. So before that, I want to prove the privacy thing. Since we do have some time, I'll show you how to prove this claim. So let me switch to Node so I can just, I thought it's better if I actually write the proof. Can you see the screen? Yeah, great. Okay, great. So yeah. So the privacy proof of this. So recall that we wanted to show that the delta M is at most delta ZR and ZR by sigma, comma 1, and ZR and 0, 1. Okay. So I'll assume that C is equal to 1. You can also, for simplicity, it's the same proof, even otherwise, it doesn't really matter. Okay, so let's call X to be, so what are the two random variables that we are interested here? So let's say X is summation I equal to 0, sorry, I equal to 1 to N, GI, sorry. So min of 1 by mi times GI plus sigma n0i. And Y is summation I equal to 0 to N min of this. So note that this has an extra Z0. So this is the extra user that we are adding. And we want to distinguish between this and this. And this is what we want to upper bound. So the first step is we use some post-processing inequality. So note what are the random variables here. So if you notice here that the random variables are V1 to VR are this random vector Gaussians. And therefore this M naught to M Mn, these are also random variables. These are the estimates of the norms, and they depend on these V's. Okay, and the G's themselves are fixed. G0, G1 to Gn are fixed. They are not random, and we assume that they are known to the adversary. Okay, so I'll use the post-processing inequality to say that I'll actually tell the adversary more information. I will also tell the adversary all these random Gaussian vectors that I use to do the estimates. And let's say I also put in the M naught here. We'll see why that is useful. So basically, I'm telling the adversary, okay, I will also tell you all the things that I used. So you can use that information to distinguish between these two. Okay, so it'll only make it, so that's why it's an upper bound. And now using these things, I can cancel all the terms which are above n, so on both sides, because they only depend on this V1 to Vn and the G's. So I can cancel GI from 1 to n on both sides. So what we get now is, after canceling, I'll get V1 to VR, M naught. I'll just get here a min of 1 by M naught, G naught. And here I'll just get V1 to VR, M naught. And here I'll just get, sorry, plus the Gaussian noise. And I'll just get the Gaussian noise here. Okay. Now, what we'll do is so now I want to claim that we can ignore, so this is an exact equality, sorry. And now I want to say that, and this is also an exact equality, I want to say that you can ignore this V1 to VR, because the only way you can distinguish between these two is look at the last coordinate. And the last coordinate is only influenced by M0. And even though M0 depends on all the V1 to VR, but since the adversary already knows M0, the adversary does not need to use this V1 to VR anymore. So it's kind of irrelevant. So this is, you can prove a formal lemma like that. I will not bore you with the details, but basically you can say that intuitively it's clear that these are useless for the adversary to distinguish. So you can just ignore them and you get this. M0 and just this plus the Gaussian noise and this. And now I'll do a rotation. I'll rotate the space so that, let's say I apply a rotation matrix U such that U times G is, basically I'm rotating so that G becomes proportional to E1. So basically I'm rotating space so that G only has one coordinate and one non-zero coordinate. This is the first non-zero coordinate. So, and it's and this is again an equality because I'm applying a fixed map to both sides. So I'll get M0 here and min 1 by M0. So the norm of G0 times E1 and M0, plus U times sigma N0I. And here you get U sigma U N0I. And I can just cancel this by using, again, I can cancel the U because it's not really canceling what I'm doing. What I'm saying is that because of, invariance of the Gaussians under rotations, invariance of N0I under rotation, you can basically, therefore U times N0I also has the distribution of N0I again. So you can write this as M0. And then you can also ignore all coordinates except the first one, because only they differ in the first coordinate and all the coordinates, they're independent now. So you can ignore all extra coordinates. I'm skipping a few steps, but basically you can prove this thing. A norm of G0, comma, a norm of G0 by M0 times E1 plus N0, 1. So now, sorry, there is no E1. This just now this became a one-dimensional problem plus sigma times N0, 1, and you want to distinguish this and sigma times N0. Okay, and so what is M0? We've seen that M0, the distribution of M0 is norm of G0 times square root of chi square R by R. So 1 by M0 or norm of G by M0 behaves like 1 by ZR, sorry, ZR, where I define the ZR random variable to be the inverse of this. Okay, so, and then, okay, so let me just do one last step. So basically we showed that this is kind of like ZR min of the norm of G0, comma ZR plus sigma N0, 1 versus ZR, comma sigma N0. Okay, and the final step is basically, it's also intuitive that if, it will be easier for the adversary if I add ZR instead of min of two quantities. So this is another lemma. You can prove that you can, it's always easier for the adversary to distinguish. Instead of adding the min of two quantities, you add the bigger quantity. Comma sigma. So, and this is exactly what I claimed in the beginning, which is, sorry. Yeah, so this is exactly equal to what I claimed in the beginning, which is n sigma. After some scaling, this is what you get. So basically, you're telling the adversary what you are, or this ZR random variable, what you sampled, and then either you shift it by ZR. Either you sample a normal distribution, or you sample normal distribution and shift it by ZR plus sigma, and you want the adversary to distinguish. Okay, so that's the privacy proof. Are there any questions?
So how tight do you think this analysis is?
Yeah, that's a great question. I think that it's it will be really nice. So let me just write here.
We just have a separate table.
Be really nice if we can get something like delta without this ZR. If I don't tell the adversary ZR, and instead just ask him to differentiate between, ask him or her to distinguish between just these two. But this is much better than this, because here the adversary has more information to distinguish, but I don't know how to prove this. Yeah.
Right.
Don't know.
Would that give you like noticeably better bounds though?
Yeah, this gives you noticeably better bounds. For example, using this bound, we know that you need like something like 30 JL projections to get good, really good privacy, or privacy curves which match almost with the DP-SGD. But if you get this buck curve, you just need some 10 JL projections. Okay, so let me just switch back. So that's the only heavy thing, and this might have gotten pretty heavy. I'll switch back to the presentation now. Any other questions about the proof? Okay. So we are back to the light stuff. Okay, so now we have showed the theoretical guarantee. Now I want to say, how do we compute these privacy curves actually, like, to plot them. So for this, we use this notion of the privacy loss random variables, which is basically this privacy loss distribution. So suppose we want to compute the privacy curve between two random variables, x, y. This is the privacy curve we want to compute. So you define this privacy loss random variables as x tilde and y tilde. So x tilde is just the log likelihood of, so this is the probability distribution of y divided with the probability distribution of x. So these are the densities, the PDF. So you take the log of the ratio of the PDFs, the densities at omega, but you sample omega from x, and in the other case you sample omega from y. So I won't go into the details of why this is the right thing to do, but let me give you some important properties of why these random variables are actually useful for us. So recall, so this is how you define it. So you can, given the explicit xy, you can compute explicitly what these distributions look like. But yeah, okay. So I won't bore you with the exact why this is, but let me give you some important properties. The first thing is it does not change the privacy curves at all. So if the privacy curve between xy is the same as the privacy curve between the privacy random variables x tilde, y tilde. And the distribution of y tilde is completely determined by x tilde and vice versa. So they have, the densities follow this equation. The ratio of the densities is always the exponential function. And there is this very simple formula to compute this. It's just the probability that the privacy curve between x tilde and y tilde has an explicit formula like this in terms of the CDF of y tilde and x tilde, or you can also just, because of this relation, you can just completely rewrite in terms of the y tilde function. Okay, so, and this is how we want to compute this x tilde and y tilde for our case. Okay, one last property which is kind of interesting is that these random variables are just uniquely determined by the privacy curve itself, not by x and y. So if two random variables have the same privacy curves, then the privacy random variables just agree, they're equal. Okay, so this is like so you can think of it as a standard way to represent privacy curve. Instead of, so it's an equivalent way to represent the privacy curve. Instead of giving this curve delta of epsilon, I can just give you these two standard random variables and say that they're equivalent. Okay, so the key lemma here is, okay, we have this, we know that we proved this theorem that the privacy curve is upper bounded by this. So now I want to compute the privacy random variables for these two things. And this is what they turn out to be. So, and this is in fact true for anything. So if you want to distinguish between NZ1 and N01, where the adversary knows Z, then the privacy random variables are given by this and this. Okay, so you can do an explicit calculation. That's what it turns out to be. So okay, that's great. So we know the privacy random variables, and therefore we can easily compute the privacy curve between this privacy curve. And now, how do we do the subsampling and how do we do composition? They also turn out to be pretty easy. So if I have a privacy random variables for a curve, then I can compute the privacy random variables for the subsampled curve explicitly using some formula. So we also know what happens to the privacy random variables under subsampling. So I won't explain. It's not hard to do this calculation. So I'll just skip this thing. So you can compute exactly the privacy random variables for the subsample distribution also. And then the really nice thing about this thing is that under composition, the privacy random variables just add up. There's no complication at all. So if you know the privacy random variables for two curves, delta 1 and delta 2, then the privacy random variable for the composition of the privacy guarantees, which is like you first do this algorithm and then do the next algorithm, even adaptively, is just the addition of the privacy random variables. So you just add the corresponding privacy random variables. This is also not hard to show. So basically, this is how we compute privacy. So now, as I said, there's an explicit formula. So after t iterations, the privacy random variables just add up, and therefore you can compute the privacy curves using the privacy random variables, or you can use this, or you can use it just in terms of you can also oops, yeah. Right. Okay, but yeah. Okay, so that is how we compute. And also, why do the moments accountant or the RDP or GDP accountants, the multitude of accounts, why don't they work? So that's because if you see this privacy random variable, so this ZR random variable behaves like it has a very long tail. So it decays very slowly. It's like at A, the density is like 1 over R plus 1. So it's not exponentially decaying density. It is a polynomially decaying density. What that means is that this, and therefore this y tilde, which behaves almost like ZR squared by 2. You should think of it like that. So it is a square of this thing. So it still has a pretty long tail. So in fact, we can show that. Just erase these things. So you can show that this y tilde has tails which are like 1 over epsilon. So the probability that it is larger than epsilon is like 1 over epsilon to the r by 2. So it does not decay exponentially with epsilon, it only decays polynomially. So the delta, it also tells us how the delta has to behave with the number of JL projections. So it behaves, so it comes in the exponent, but it only decays polynomially. So this is also tells us some intuition about how the number of JL projections will affect our privacy loss. So because of this, like only R by 2 moments, or not even R by 2, but something like less than R by 2 moments exist. The moments higher than that don't exist, and exponential moments don't exist. So therefore, you can't use moments accountant. RDP accountant also requires large moments. The GDP accountant, which uses the central limit theorem to approximate, also fails. It just does not converge. So what we instead do is numerical convolution using FFT. So we actually truncate this distribution appropriately and discretize it, and then convolve them using FFT, which is efficient. And then we finally compute the delta using this formula. Okay, so this is how the privacy curves look like. So as I was telling Thomas that, with JL10, it's still pretty bad, but JL30 or JL20, they get very close to, so this dotted line is the DP-SGD vanilla. And we see that already with 10, 20 projections, you get pretty close privacy.
Sorry, quick question here.
Yeah.
How are you obtaining the curve for the DP-SGD vanilla?
This actually I also computed using this numerical convolution using FFT.
Nice, thanks.
Yeah. So that's because this is more accurate than even moments accounting and stuff.
Yeah, exactly. That's what I was.
Okay, so let me show some experiments. So if we train a neural network on actually an LSTM with some embedding layer, it has about 600,000 parameters on this IMDb dataset, which is an NLP task. So what we see is this. So this is the DP-SGD algorithm of Abadi et al., and this is the TensorFlow privacy implementation. And the batch size is 256. This delta is fixed. So, and the plot here is color-coded in epsilon, and this is time versus accuracy. You see that, this takes really long time. This is like 10 to the 5 seconds, of the order of 10 to the 5 seconds per iteration. That's like about, and then this whole training took us 2 days. Whereas this thing, these are our algorithms, the JL algorithms, and there are 10 projections, 20 and 30. So the 10, as we've seen, the privacy is bad. So you see it is going to very high values of epsilon. But the JL 20 and 30, they're pretty nice. They're like at this range, and JL 30 is pretty similar to the privacy. As we have seen, the privacy curve of JL 30 is very similar to DP-SGD, but you see that there is a big gap here, like almost 2 orders of magnitude in terms of running time. Okay, and it turns out the speed up is typically should be like proportional to the batch size by JL dimension. But I don't think this is the real speed up that we should expect. I think that the TensorFlow privacy is doing something wrong. It should not take this long, because even if you compute the per sample gradients one by one and then remember them, it shouldn't take this long. So the speed up should be more like this, but that can still be significant if the batch size is large. Okay. And in terms of memory, we are actually pretty similar to non-private SGD. So we don't really consume much more memory. And we also experimented with much larger networks, like 32 million parameters, and it works. Okay, any questions? Okay, so this is another interesting plot, which is also like hinting at what, which suggests or answers somewhat Thomas's question, which is like, can we prove better privacy bounds? So one thing we could do is first like understand how the JL dimension affects, like for a large, so we know that as R tends to infinity, the JL algorithm with R projection should converge to the normal DP-SGD. And so we want to see how quickly does it converge in terms of behavior or the training characteristics. So we look at how many epochs versus the test accuracy curve. And I did many, many runs to remove the randomness and average. So this is the non-private one. So basically it achieves very high accuracy very fast. And this bottom curve, which you can't really see, is in black is the DP-SGD vanilla, or the normal DP-SGD. And you see that, so this is JL1. JL1 behaves very differently from the normal one. In fact, it's closer to non-private. But as already with JL3, it is very close, and JL10, they are just indistinguishable from DP-SGD. So another interesting use for this algorithm is like, let's say you actually don't care about privacy. You're really experimenting, how well DP-SGD does. So you're still in the experimental stage, and you want to set different parameters. You want to try different architectures, and you don't really care about the actual epsilon. You want to know how well DP-SGD does. Then what you can do is just run our algorithm with JL3 and see how well it does. It's much, much faster than DP-SGD. And you can find the best architecture, you can tune hyperparameters and do all that. And at the end, if you just want a good epsilon in your books, just use DP-SGD at the end. Because DP-SGD also, the other reason why it is not really used so much is because it makes it's a nightmare to tune all the hyperparameters when your algorithm is like already so much slow. So this is another advantage for our algorithm, that it behaves very similar to DP-SGD, even though unfortunately we don't know how to prove really good privacy bounds as good as DP-SGD with small JL dimensions. But empirically, you can see that it behaves almost identically, even with just 3 or 4 projections. Okay. So then there's the new framework called JAX, which I did not know about before, but it has some amazing compiler magic. So it has these 2 primitives called VMAP which is a vector map operator. What this means is if you want to compute the same function on multiple inputs, then it's this VMAP operator does it much faster than just calling n times this function in a loop. So it does some kind of parallelization and some optimization, and actually in terms of like, it actually speeds it up by, a factor of 100 or something like that. So it's some crazy operator which does like some compiler magic to really speed up this thing. And this, you can use it to speed up DP-SGD, because DP-SGD is computing this per sample gradients, which is like the same function you're computing on different inputs. So, and that's what some people did. I'll come back to that. And there is another operator called JIT, which is some just-in-time compilation operator. It just seems to speed up any code. Like it's just, yeah. So anyway, so there are these two operators in this JAX. And so there's this paper by Pranav Subramani, Nicholas Vadivelu, and Gautam Kamath, where they use JAX to speed up DP-SGD, and it does really well. Like, actually, at least in their experiments, it comes to very close to non-private SGD in training time. So maybe the story changes a little bit after this JAX thing. I also implemented this DP-SGD-JL in JAX, and we also observed similar improvement. It just makes everything much faster. Like much faster than what TensorFlow is doing right now. So we also observe that there is not too much difference in terms of time once you all use all these crazy operators and stuff in terms of DP-SGD versus our algorithm. But what we observe is that our algorithm still wins in memory. Why is that? Because DP-SGD, even if you use this VMAP, what this VMAP operator is doing is it's computing. So DP-SGD will compute all per sample gradients in parallel or some kind of parallel. What that means is your memory, the memory will be roughly the number of parameters of your network or the model size times the batch size, which is kind of bad. If your batch size is 256, you're saying, okay, if my model is barely fitting in memory, I can't afford to like actually compute all the gradients. So for large networks, this is not really feasible. But the JL never actually computes all the per sample gradients. It only computes estimates for the gradient norms. So it still wins in terms of memory. And memory is important for training neural networks. But I think more experimentation is needed in this space with this JAX and stuff. Okay, so let me conclude. So we given this DP-SGD-JL outcome, and the key idea is that you can estimate per sample gradients using JL projections instead of computing them exactly. And it works on any architecture. It's not dependent on a specific architecture. And in terms of memory, it's similar to non-private SGD. And in terms of privacy versus accuracy, we've seen that depending on the number of JL projections, you can actually match DP-SGD. So you need something like 30 JL projections to actually be equal. And it's much faster in terms of speed. So one open question is what Thomas asked: can we improve the privacy analysis of DP-SGD-JL? If we can actually prove, we've seen that empirically it behaves very similar, so maybe there is a better privacy analysis. But the current privacy problems that we can prove for small JL dimensions is bad.